Hey everybody, it's Mrs. Crumbliss. This is our last set of notes for this unit. Of course, I have the numbers wrong. It's going to be 4.5, 4.7, 2, 5.9, 5.10, and 5.11. Remember that your coffee cup cover material lab should already be turned in, and you should be working on the at-home practice as we go. Please make sure that you're doing the little packets that I have for you, like the reaction mechanism practice and the determining rate laws made easy. They are set up and designed to help you understand these concepts and topics. So they should be providing a lot of clarity. I also loaded the answer keys to them that you can look at, but please try to do them on your own before you use the answer keys. You can certainly work with someone else, but yeah, just see what you can do on your own first. This is probably the last lecture I'm going to record. Well, this is the last lecture I'm going to record, but I'm probably not going to send you another video. So after today, on Thursday and Friday of this week, I'm going to open 2 labs for you to work on. There's a nuclear simulation, and there is a determining rate law. These are both going to be dry labs. The nuclear simulation is just log on, roll some dice, take some data, make me some graphs. The determining rate laws is actually watching a video of someone doing the lab and taking the data. Make sure that you read through everything that I give you carefully, fill in all the data that you need, make the appropriate graphs, and answer the questions that's asked of you. This is going to be a lot about following directions carefully. I will be back on the 23rd, and at that point, the only thing that should be due is your nuclear decay lab. That one should be fairly cut and dry. The determining rate law isn't due till the 1st or 2nd of March, so this one is due February 23 and 24. This one is due March 1st and 2nd. So that should give you an opportunity to be able to ask me questions on this one. Like I said, this one should be fairly cut and dry. Again, reach out if you have any questions. Let's go ahead and get into the last little bit of notes for this unit. We're going to talk elementary reactions, introduction to reaction mechanisms. If you remember me talking in class, I love me some reaction mechanisms. Mechanisms and rate law, steady state approximation, multi-step reaction energy profiles, and finish up with a little bit about catalysts. So let's start with the this energy diagram. So we're going to look at this little energy diagram we have over here. And if you notice, it's got like multiple bumps on it. These multiple bumps are showing us, let me circle back and answer the actual questions on the paper. So it says, what does the balance equation show? A balance equation shows the ratio of reactants to products. What is present at the beginning and at the end of the reaction. But that isn't all, but is that all that happens in the reaction? No. There are lots of different small reactions that can happen. Within the overall reaction. And the process of looking looking for or examining these small reactions is called the reaction mechanism. And these small reactions are the same as our elementary reactions. We talked about when we were in Unit 6. So each of our little bumps on this reaction profile is showing us an elementary step. It's saying first I'm going to make this, and then I'm going to make this new product, and then I'm going to do the hard work and make my final product. So that's kind of why our reaction mechanisms don't always look like they just have one. Often they have multiple humps. So the process in which a reaction proceeds is called its reaction mechanism. The process can be several steps. Each step is called an elementary reaction or elementary process, and we've talked about those already in Unit 6. So let's talk about molecularity. This isn't something we've talked about before. Molecularity is just looking at how many molecules are involved in any one step of the reaction. So we have three different kinds of molecularity. We have unimolecular, and this is a reaction with a single species. And we're talking about the reactants. So in our elementary reactions, we know that our reactants can be the products of the last step. So this is the reactant of whatever step we're looking at. If that reactant happens to be only one species, it's called unimolecular. We have bimolecular ones that are two species. And then we have termolecular, which is going to be three species. Most of our reactions are going to be these two. The termolecular ones are really rare because it would require three molecules to collide simultaneously with proper orientation and energy. And that just doesn't happen very often. It's not very often you can get three molecules to hit exactly like they're supposed to. So that's why most of them are unimolecular or bimolecular. So we can use the molecularity to help verify the mechanism that's been proposed. So that's why molecularity becomes important, because it can help us kind of figure out whether our mechanism is appropriate. Molecularity is a theoretical term, and it can't be used to determine a reaction rate or the order of any specific steps, but it's just as a verification. So the rate laws can be written for each elementary step from the balanced equation. if the individual step is given. So if we have a unimolecular reaction, this is what its rate law is going to be, and that means that this is going to be first order. If we have a bimolecular reaction, it could have two options for what its rate law could be, because it could be squared, it could be A squared, it could be AB, depending on if I have the same reactant twice or not. And these are both going to be second order. And then our termolecular ones have a lot of different options, and these are typically going to be our third order reactions. So like I said, we can't actually write the mechanism from it, but it can give us some verification of whether or not the mechanism we're using is correct. So we also need to talk about what a rate limiting step is. I kind of refer to this all the time. I kind of tease you about your grade limiting step or your grade limiting factor. Well, this is where that phrase I use all the time comes from. And what it is the reaction can only occur as fast as its slowest step. So if I'm headed through like this toll booth scenario, I have toll A over here that is slowing everybody down. I can't get through this whole process any faster than toll A allows me through. So in this case, toll A would be my rate limiting step. If I look at my second scenario, toll A is now quick, but toll B is where everything is bottlenecking. And so toll B will be my rate limiting step. So the rate limiting step can change, it can be different, but it is nothing can go faster than that slowest step. So the overall reaction cannot occur faster than the slowest step in the mechanism. And I usually refer to in our family as my son Sam being our rate limiting step. He takes forever to tie his shoes. Don't know why. He's in his 20s, still takes forever to tie his shoes. We can never get anywhere faster than Sam can get his shoes tied. So he is constantly and forever my family's rate limiting step. I love him with all my heart, but he's slow at things. And I'm certain in your family you can think of what your rate limiting step is. All right, so let's turn to our first ICP in this section. We're going to go to ICP 13. This is 5.5. We already did 5.5, but we couldn't do this question because it's talking about mechanisms. So we had to wait till we got through mechanisms to do it. It says the reaction above is carried out at a constant temperature inside a rigid container. Based on this mechanism, what would be the most likely reason for the different rates of these steps? So if we look at these two steps, they look pretty similar. We have two bimolecular reactions. We have, so they're both bimolecular. They're all gases, so they have the same state of matter, which is another thing that can speed up our steps. And so it has to lead to the energy. So the amount of energy required for a successful collision must be greater between the reactants of step 1. So that is kind of what you need to think about in your rate determining step. Is it the molecularity of it? Is it the states of matter of it? Is it the energy? Energy is kind of our default most of the time. All right, so let's look at reaction profiles. So a lot of our reaction profiles aren't as simple as we've made them so far. Many times we have to have each elementary step exhibited. So we have our reactants and our intermediate, our transition state, and then the products of our first step. Then we have to go overcome another activation energy to get to our transition state of that step and the products of our second step. And this one actually has a third step. So this gives us an idea of how much energy is required in each portion of the steps. Whatever step has your greatest activation energy is going to be your slowest step. So the step with the greatest activation energy is the slowest step. So there are a few things that we can look at in our reaction mechanisms, and the first one is called an intermediate. An intermediate is formed in one step, then consumed in another step. No, sorry, I'm trying to erase this and it's not working. Just a second. It will not be a reactant or product. And when we look at our reaction profiles, a lot of times the lulls in between, those reactants of each step will have intermediates in them. Just looking at my notes to see if there's anything I haven't already said. No. So these intermediates are something we just need to be able to identify when we're looking at our mechanism. What in there isn't actually a reactant or a product that shows up and is then consumed and it never ends up coming back out of the reaction. You need to not confuse a intermediate with a catalyst. A catalyst is put in and not consumed, and it comes back out as it went in, where a intermediate is created and consumed and disappears. So neither are in the overall reaction. A catalyst is in the beginning of the reaction, and the very end. Intermediates are formed and consumed during the course of the reaction. And remember that a catalyst lowers the overall energy of the reaction without being consumed. So it comes back out the other end. Let's look at in class practice 16. Here we are looking at our very first real mechanism, and it's more of a mechanism than what we were doing before when we were flipping things, because it tells us my slow step, my fast step, my fast step. So we only ever have one slow step. And if we look and we added all of these together, we would get our target reaction, just like we did previously. So the first thing that this one asks us is, what are our intermediates? So I need to look at my overall reaction and compare it to what I'm seeing down here. So I see hydrogen peroxide and hydrogen peroxide. I see iodine and iodine. I look at this HOI. I don't see it anywhere up in my overall reaction. So I'm going to highlight that. My hydroxide is similar. I don't see that anywhere in my overall reaction. Actually, let me highlight hydroxide a different color. So then if I look, does my HOI then disappear somewhere? And it does. It's used right there as a reactant, and it goes away. And then, weird, I have another OH. So, and that's not in my overall reaction. But if I look, I have two OHs here in these reactants. So that means that my OH, my hydroxide ion, is an intermediate, and my HOI is also an intermediate, because they are made and consumed. The next part of this question says, sketch an energy profile with 3 steps of the mechanism and clearly label the rate determining step. So I did mine like this. So my first one is going to have my highest activation energy, because this is my slow step. My other two have much lower activation energies because they are not my slow step. So let's talk about reaction profiles of multi-step reactions. So this is looking at 5.10 and 5.11. So when we look at these, the number of humps in the reaction tells you how many steps are in this reaction. So this reaction is 2 steps. The largest hump is the slow step. So this means our first step is slow. And we can actually look at this and label a lot of things. We can look at the fact that here and here are our transition states. The difference between our reactants and our products. So here is going to be our delta H. Between reactants and our first transition state is going to be our activation energy. Here's our intermediate and the next transition state. So this is our second activation energy. This is our reactants, and this is our products. So because my delta H is higher than my reactants, this is going to be endothermic. And we can just tell a lot about the reaction from just this small energy profile. I feel that once we get into multi-step reactions, these energy profiles become more and more telling of what's really happening in the reaction. So we can also look at catalysts in our multi-step reactions. And if you look at my tiny little figure up here, he got real little. The difference between putting in the overall reaction and putting in the catalyzed reaction, you can see how my first step becomes really low. It becomes my slow or my fast step, and my second step becomes my slow step because I catalyzed the reaction. The catalyst is also what helps form the intermediates and everything else because it changes the mechanism from the original profile, which was just one big hump, to this multi-step mechanism with multiples. There are different kind of catalysts that we can use. We can use a homogeneous catalyst. So this is when the reactant and catalyst are in the same phase. So often they're dissolved in the same solvent. We also have heterogeneous. These are in different phases. Often it's a gas passing over a solid. And then we have enzymes, which is this is the IO logical. And is a lock and key model. So those are our three types of catalysts that we can use. So let's go back to our in-class practice. Let's go to number 25. We're just going to finish up the little endy bits of this one. So this first one is just having us draw a reaction mechanism. We're going to start at 20. We are going to have a transition state at 80. We are going to have an intermediate state at 50. Another transition state at 90, and our reactants at 5. So we're going to go up and down and up and down. Okay, not my prettiest reaction profile. The only question on this is how many steps are in this proposed reaction? And there's 2, because I have 2 humps. Which step's going to be my slow step, the first step or the second step? It's going to be second step. All right, so let's look at, oh wait. On the graph below, illustrate an endothermic reaction that proceeds via a 3-step mechanism where the second step is the rate determining step. So I'm going to start with my reactants down here. I'm going to do my first one, my second one, my third one, and make sure that my products are higher than my reactants. And that should be what that reaction mechanism needs to look like. Let's go ahead and turn to 27. 27 is again giving us one to draw, but here it's giving us our products first, which is kind of goofy. So here's our products. Oh, no, I just read it first. Here's our reactants. Here's our transition state. So it says, now add a dotted line that represents a catalyzed reaction that occurs in 2 steps. The energy of the first transition state is at 75. So there's 65, 75. releases 40 kilojoules of energy. So I have to go down 40 kilojoules. So 5, 10, 15, 20, 25, 30, 35, 40. And the energy for the second one is 50 kilojoules. Oh, we're going to have to move that one over a little bit. And then 50 kilojoules is there. So remember that I start at the same spot. I go up, down, up, and end at my products. Let me make my lines a little better. All right. So there is what this would look like as a catalyzed reaction. 28, here is a mechanism. I need to write the overall mechanism. That means I just need to add them together. What goes away? What doesn't go away? So if I look at my reaction, I have A and B. A is always there. It's going to be like my permanent reactant. B, I have a B here and a B here, which means I'm going to have 2B because I have 2 B's in my reactant side. My C is a reactant or a product on one side and my reactant on another side. So that's going to cancel out. My D does the same thing. It's a product and then a reactant. And then I have 2 E's in my reactants. So my overall reaction is going to be A2B yields 2E. My intermediate here is going to be C. And then D, it says A, students suggest that A is a catalyst for this reaction, but they're wrong. Explain why and identify the catalyst. Well, the catalyst gets consumed and reappears. A is a reactant and is only used up, it never reappears. A is a reactant that only gets used and does not reappear. D, on the other hand, comes in as a product that was not made in the step before. It comes in as, a reactant. And then reappears as a product. So because it appears as a reactant and then goes away, is regenerated as a product, that tells me that it is my catalyst. So this reaction has a catalyst as well as an intermediate. And the last thing says, propose the rate law that is consistent with the reaction mechanism provided. So if you look at the reaction mechanism can only be from my slow step. So my rate is going to be equal to K, concentration of A, concentration of B. I know that in my reaction, it's 2B, but this isn't going to be B squared because in my slow step, there's only 1B. So you have to be really careful of that because only your slow step can allow you to write your reaction rate. So how do we know if a reaction mechanism is plausible? The rate law must be able to be derived from the rate determining step. So your rate law has to match what's happening in your rate determining step. The stoichiometry must be obtained with all steps when all steps are added up. Each step must balance like any equation. All intermediates must be consumed and made. All catalysts must be used and regenerated. So let's look at question 17 in our in-class practice. This set of notes has just a lot of in-class practice. All right, so here is a diagram. It says the particle molecule model shown on the side represents the proposed two-step mechanism for the deconstruction of ozone in the upper atmosphere. Based on the models, what represents a species that acts as a catalyst in this reaction? So what do we have up here that is a reactant, gets used, and then comes back out the same as a product? And that's going to be this little guy here, because if you look, he's a reactant, he's a product. Everywhere else in my products and reactants, he's bonded with something. So my chlorine is going to be my catalyst. Based on the proposed mechanism, what is the balanced equation for this overall reaction? So I just went ahead and wrote out each reaction. So I'm going to have O3 plus Cl. It's going to give me O2 plus OCl. That's already balanced, so I don't need to worry about it balancing it. This is my slow step. And then I'm going to have OCl plus O3, which is going to yield Cl plus 2O2. And this is my fast step. If I add these together, I'm going to get 2O3 yields 3O2 because my chlorine is a catalyst and my OCl is going to be my intermediate. Number 18, if I look at this reaction mechanism, are there any catalysts present in this reaction mechanism? Are there anything that comes in as a reactant and then comes back out as a product? And the answer is no, nothing does that in this reaction. Are there any intermediates in this reaction? So something that is created and then is gone? And the answer to that is yes, and it's going to be oxygen. Because if you look, I have an oxygen here and an oxygen here. And so because it is created and consumed, it's going to be my intermediate. What is the overall reaction? So if I add this together, I'm going to have 2N2O gas yields 2N2 gas plus O2 gas. So there's my overall reaction for this mechanism. Number 19 just asks for an overall reaction of the mechanism, which we already did in the last step. Is this the same reaction? Oh, no, this is a different reaction. Never mind. So what can we cancel out of this? So NO is here and NO is here, so that one's gone. O3 is here, but it's nowhere else, so O3 is going to be my first reactant. NO2 is a product, NO2 is a reactant, so those can cancel. I have two O2s in my reactant side. And in my product side, the only thing not accounted for is this poor little oxygen. So it's going to be O3 gas plus O gas yields to O2 gas. And then in number, no, so this is, never mind. Okay, so if there are multiple steps in a reaction, how is the rate determined? I kind of already talked about this. When we look at multiple steps, the rate law and relative speed of a reaction is dictated by the overall rate law, which remember is determined experimentally. If the reaction is an elementary reaction, the rate law can be based directly off molecularity. So that's how we're going to look at how those different steps of the reaction determine the rate law. Now we just need to finish up our in-class practice. So let's look at number 20. It's cyclopentane is an alkane with a ring structure that reacts with chlorine to produce C2H9Cl and hydrochloric acid. So here's my following reaction, my steps, and what is fast and slow. Write the overall reaction for this equation. So when I look at what I can cross out, I'm going to have C5H9 plus Cl2. Oh, no, this is C5H10. So my C5H9 is going to cancel here and here. My chlorines are going to cancel there and there. My Cl2 is left. My C5H10 is left. On my product side, I have my hydrochloric acid, and I have my C5H9Cl. It says write the rate law for this reaction that is consistent with the mechanism. So our slow step is right here. So that's going to be where we look to be consistent with the mechanism. And the rate here is equal to K, the concentration of chlorine. The first step is slow, rate determining. And the only reactant for that step is Cl2. A student claims that Cl2 is a catalyst in the reaction. Explain why this claim can't be true. This can't be true because the chlorine is consumed in the reaction. It never regenerates in any place, and it's our beginning reactant. So that is going to be, it can't be a catalyst. All right, so here's a question 21. The rate law for the decomposition of hydrogen peroxide shown below is determined by the rate law, determined to be rate equals K, the concentration of hydrogen peroxide. Identify the slow step in the process in the proposed mechanism below. So what we know about slow steps is the slow step is going to be equal to the rate law of the elementary step. And if we look at what our overall reaction has and what each step has, we can say that step 1 is our slow step because the rate law for step 1 matches the experimental rate law. And if you notice step 2, it can't be step 2 because OH is in step 2. OH would have to be in the rate law if step 2 was the slow step. Now if we look at question 22, it says the rate law for the decomposition of dinitrogen pentaoxide shown below is experimentally determined to be a rate of K equals the rate equals K, the concentration of dinitrogen pentaoxide. A student claims the reaction occurs in a one-step mechanism. Do you agree or disagree with the claim? We would have to disagree, because if the rate law or if the reaction occurred in one step, the rate law would be rate equals K dinitrogen pentaoxide to the second power. And it's not. Experimentally, it came up to only the first power. So this can't be a one-step mechanism. There has to be other mechanisms in there for that to be the rate law. All right, so number 23. We are looking at a reaction is proposed to take place in the following elementary steps. If the rate law for this reaction is found experimentally to be AB, rate equals K, AB to the second power, C to the second power, what must be the slow step in this reaction? So what I did for this one is I just wrote the reaction rate according to each step. So for step 1, rate equals K. We're going to give that a little 1, so we remember it's step 1. Concentration of AB, concentration of C. So this is not slow because it does not match. Step 2, rate equals and we're going to call this K2, so remember it's the second. D, concentration of D, concentration of C. But because D is the product here, I can take my D here and substitute in the rate law for step 1. So this is going to become rate equals K C, which comes from here, concentration of AB, concentration of C. And if I put that all together, my rate is equal to K, concentration of AB, C to the second power. So it's closer, but we're still not there because we don't have AB to the second power. So it's not step 2. So now I need to go to step 3. For step 3, my reaction is going to be, or my rate is going to be, rate is equal to K3, concentration of E, concentration of AB. And now, because E is my product of step 2, I can take E and substitute in what E equals from step 2. So that means I'm going to say rate is equal to the concentration of AB, C to the second power, concentration of AB, which is going to equal K, concentration of AB squared, concentration of C to the second power. So step 3 is the slow step. And this is called steady state approximation, meaning that I can just take whatever my rate is for a product and put it in to estimate what the rate is for a later step. And should be to our last problem. So this one's kind of long. This one says the nitrogen dioxide is produced by a byproduct of the combustion of fossil fuels in internal combustion engines. At elevated temperatures, nitrogen dioxide decomposes according to this equation. The concentration of the sample is monitored, and it decomposes as it decomposes and recorded in the graph opposite. So it's actually a little bit below. So there's the first graph that we got that's just concentration versus time. 2 other graphs were derived from the original data. So I have one over the concentration of time, and I have the natural log concentration of time. So explain how the graphs indicate the order of reaction. So the most linear graph is 1 over the concentration of nitrogen dioxide versus time. So this indicates a second order reaction. That means our rate law is going to be K concentration of NO2 squared. And we know that because we determined that this was the rate using the data. I says, consider the 2 possible mechanisms for this decomposition reaction. So I have 1 mechanism and I have mechanism 2. I says, is the rate law described in mechanism 1 shown above consistent with the rate law you wrote in part B? And the answer is yes. Step 1 is slow and has a rate law consistent with the graph. In step 2, no nitrogen dioxide molecules are involved. So that can't be the correct mechanism. And then II says, is the rate law described in mechanism 2 shown consistent with the rate law you wrote in B? And the answer to that is yes. Step 2 is slow, so it is the rate determining step. And 1 nitrogen dioxide is involved. But if step 2 depends on N2O4 produced in step 1, so it is dependent on another nitrogen dioxide molecule. So step 2 is slow, so the rate determining step, and 1 NO2 is involved, but if step 2 depends on the N2O4 produced in step 1, so it's dependent on another NO2 molecule. So if we use that steady state approximation and substitution method, then it's going to be consistent with the rate law we wrote in B. That is all we have for this unit, y'all. This is all of the notes. Please answer the questions. Ask me any questions you have, and I will see you soon.